In this video, we are going to talk about what I call the Aunt Grace scenario. So I want to begin by answering scenario 2 from the last video. So let's answer scenario 2 from the previous video. So let's first remind ourselves, well, what is that scenario saying? So in the initial example, there's an anonymous donor who's gifting $1 million for a scholarship fund that's deposited into an account that earns 5% interest, continuously compounded annually. But in scenario 2, it's slightly modifying that. And it's saying that the scholarship is going to award one student $40,000 per year continuously. And they're going to increase that by 3% per year, continuously compounded, to account for higher living costs. And the question we want to try to answer now is, how much would the anonymous donor need to initially gift? Because maybe that $1 million isn't going to cut it, like the initial example said. How much would they need to give initially to fund this scholarship forever? Okay, so one thing I want to note about this is that our textbook calls this wealthy donor Aunt Grace, who is so generously funding this income stream. In my example, it's this scholarship fund forever. Okay, so let's talk about how we can start to tackle this question. Ooh. So the idea is the donor puts some amount into, let me space that out more, into an account now, and then they just leave that alone. So all that's going to happen is they're going to earn interest, and it earns interest. So they're not going to add extra money later. They just have to put some amount into it now and then just let it go and earn interest. Okay. The other piece to this is we need this account value to match the scholarship in quotes. I'm going to write payouts. So the amount that needs to be withdrawn to fund the scholarship. And this needs to happen forever, because that's the scenario. We want this initial donation to last forever, so it doesn't run out. All right. So this means, in other words, that we need to find the blank of the scholarship award payouts. So there's a certain term that goes into the blank here. And I want you to pause the video. It's a term from section 7.4 on continuous income streams. And I want you to think about, well, what is that term that goes there? Pause the video for 1 minute to think about this. So 4, 3, 2, 1. Pause that video. So some value. Find what value of the scholarship payouts. All right, so hopefully you did that. Hopefully you paused it for about a minute to think about, well, what goes in that blank? So we are interested in knowing, in a sense, how much those scholarship withdrawals are worth now. How much we'd have to put into an account now that earns interest so that its value matches the scholarship payouts. And that is the present value. So we want to know the present value of the scholarship award payouts. Okay, so we're going to need to use the formula for present value. So let's recall what that is. So present value, which I'll call PV, is an integral, typically we'd write that it goes from a to b, but a in this case is 0, because this is the starting time. So the starting time is a equals 0, and the ending time, because we want it to be forever, means that there is no end time. And if there's no end time, which means we are going to infinity here. And then recall the formula was r of t times e to the r times, and what goes in the first spot here in the parentheses is a. Remember, a is 0. That's our starting time. So 0 minus t dt. So the exponent is going to simplify to just negative RT. All right. So let's start to plug in what these values are from our example. So in our example, I'll put an arrow here for each value. So R of t, this is the value of our income stream. So the income stream here is based off of, well, how much are these people going to be withdrawing for scholarship? And the question says that, oh, they're going to be withdrawing $40,000 per year continuously. But that value is going to increase by 3% per year, continuously compounded. So that's suggesting that we're going to use that PERT formula, because we have continuously compounded interest for the scholarship payouts. So we are going to use P e to the RT, and now let's start to plug in for this. So P represents the initial payout rate, which is, I'm just going to write 40, even though it's 40,000, and I'll just keep track of the units later. So 40 is the initial amount, and then times e to the r, my interest rate. So that's the interest rate for how much the scholarship amount is increasing each year, which is 0.03, and then t, and then I should write the units. So the units here are $1,000 per year. So I'm going to write K dollars per year, where the K stands for 1,000. So usually when we say something like 20K, that means 20,000, or 60K, 60,000. Alrighty, so there's one other thing that I'm going to have to plug into this formula, which is this R in the exponent. So this is where we have to be a little bit careful. So the R that gets plugged into the exponent is the interest rate of the account that the money gets deposited into. And that was given to us at the start of the example. The interest rate of the account was 5%. So that's different than how much the scholarship increase is from year to year. That was 3%. So this R, the one in the exponent, whoops, is 0.05. So this is the account interest rate. So that's a really important distinction. If you're a little bit unclear on why those two values are different, I'd encourage you to pause the video at this point for about a minute to go back and look at the original problem again and see that you understand that there are two different there are two different percentages here. One that refers to how much the scholarship is increasing each year. That's that 3% value. And the other percent is how much interest rate is the account earning, and that's that 5%. Okay, so let's plug in now to our formula. All right, so if we do that, and I'm going to zoom out a little bit so I can see better. So what we'll get is, we will get the present value equals integral from 0 to infinity, R of t, which is 40 times e to the 0.03t, and then times that e to the negative RT. So that's going to be e to the negative 0.05 t dt. Okay, so we can see that this is an improper integral because of this infinity. So maybe it converges, maybe it doesn't converge. Okay, so let's evaluate it. Well, we can simplify this. So e to a power times e to a power. So using exponent rules, we add the exponents, and we'll get e to the negative 0.02 t. Okay, so we are ready to do this antiderivative. And doing that, we'd get the 40 just stays there because it's a constant multiplying this. And then antiderivative of this e term is going to be e to the negative 0.02 t over negative 0.02. And then I'm going to have to plug in the 0 and the infinity. Okay, but remember technically that when we have these improper integrals, I need to replace the thing that makes it improper. In this case, that's the infinity with a variable, and then take the limit. So in the improper integral section, we would replace the thing, in this case the infinity, whatever is making it improper, with t, and then take a limit. In my problem, I already have a t in my expression, so I'm going to need to pick a different variable. So let's replace this with k, since there's already a t in the problem, and take the limit as k goes to infinity. So that'll give us the limit as k goes to infinity of, and if you divide 40 by negative 0.02, we'll get negative 2000. And we have e to the negative 0.02 t, and then 0, and then a k up there. All right, so I'm continuing this on the next page, so I have some more room to write. So now let's plug in. We get the limit as k goes to infinity. With the negative 2000, since that's multiplying this term, I'm just going to keep that factored out. So let's keep the negative 2000 factored out. And then I'm going to plug in the k and the 0. So if I plug in k, we get e to the negative 0.02k minus what I get when I plug in the 0. And when I plug in 0, we're going to get e to the 0. Okay, so notice again that the negative 2000 I have just factored out. Okay, so from here, I am ready to evaluate this limit. And with the limit, first thing I do is I typically plug in and see what happens. So that's going to give me negative 2000 times e to the negative 0.02 times infinity, which is negative infinity, and then minus e to the 0 is 1. And e to the negative infinity, we've seen this before a couple times now. E to the negative infinity is equal to 0. Okay, so simplifying this, we get negative 2000 times negative 1, which is 2000. And what are the units here? The units of money in this question were thousands of dollars. So I'll write K for thousands of dollars. And that's it. That's how much would have been needed to be deposited in the account at the start to fund this scholarship. Okay, so 2000K is 2,000,000, which is 2 million. So this is $2 million. This would fund our scholarship forever. If that much was donated at the start and it would earn that 5% interest rate, that would be enough to keep withdrawing the amount needed for the scholarship fund forever, so that the account would never run out. So in terms of our goals for this section, we have now talked about the second goal. We did this example, which I referred to as the Aunt Grace scenario, because our textbook calls this wealthy donor Aunt Grace. And in the next video, we will do another perpetuity example, but up the difficulty a little bit.